Far-field speech recognition is a challenging problem because a limited number of far-field speech corpora are available. Far-field speech can be created by convolving clean speech with reverberation effects and adding background noise. The reverberation effects are characterized by the transfer function known as room impulse response. For example, when we have a clean speech like this,
the king seemed only pleased with everyone present.
We can convolve with room impulse response to create a reverberant speech.
The king seemed only pleased with everyone present.
By adding background noise, we create a far-field speech.
The king seemed only pleased with everyone present.
Prior room impulse response simulators use room geometry, sound absorption, and sound deflection coefficients as input and generate room impulse responses by simulating occlusion, specular, and diffuse reflection. There is still a gap in the reverberation effect simulated by the existing room impulse response simulators and real-world room impulse response. We propose a complementary GAN-based room impulse response generator that is trained on real-world room impulse response. The energy distribution of the room impulse response generated using our IR-GAN is more closer to the real-world room impulse response when compared to the existing acoustic simulators. Our IR-GAN can parametrically control acoustic parameters learned from real room impulse responses and generate synthetic room impulse responses that can imitate different real-world environments. We use acoustic parameters such as reverberation time, direct-to-reverberant ratio, early decay time, and early to late index to control room impulse response generation. In this video, we demonstrate how we increase the direct-to-reverberant ratio of the room impulse response from low to high. When the direct-to-reverberant ratio increases, the direct sound becomes stronger than the reverberation. We evaluate our IR-GAN on the Cardi LibriSpeech far-field ASR recipe. We augment far-field speech training set by convolving clean speech from LibriSpeech dataset and do its different set of room impulse responses and adding environmental noise from BUT reverb dataset. We train time-delayed neural network on the augmented dataset and test the model on real-world far-field speech test set. We can observe that our IR-GAN outperforms the state-of-the-art Geometric Acoustic Simulator by up to 8.95%. The Geometric Acoustic Simulator uses room dimension, loudspeaker, and microphone location to create room impulse response for a particular scene, while our IR-GAN uses acoustic parameters to generate room impulse responses. When we combine the room impulse responses generated using our IR-GAN and Geometric Acoustic Simulator, we observe total reduction in word error rate by up to 14.3%. In summary, we present GAN-based room impulse response generator to generate realistic room impulse response using acoustic parameters. Our IR-GAN outperforms the state-of-the-art Geometric Acoustic Simulator by up to 8.95%. We show that combining synthetic data generated using our IR-GAN with existing acoustic simulator can boost the performance of the far-field ASR system. Thank you.